This is the most optimal design that we derived for this particular budget constraint. So that is the basic HLD of a search autocomplete system. In today's video, we will be constructing the high-level design of our search autocomplete system similar to the Typeahead suggestions provided by Google Search. Now, if we go through the design specifications, we can conclude that the system needs to return the top 5 suggestions for every keystroke within 100 milliseconds while processing around 10 million search queries per day. So to achieve this low latency, the design uses a tree with pre-computed top K suggestions while the expensive aggregation and tree rebuilding happens offline. Now let's go through the design and start constructing the actual architecture. First, we begin with a client. As we know, everything starts with a client, and a client can be a web browser or a mobile application. Now, whenever a user types a character into the search box that we have, the client sends the current search prefix to the backend. For example, if the user types app or app, the client sends app as the prefix. If the user continues typing and it becomes apple, another request is generated for the new prefix. Since every keystroke can result in a request, this is a very high latency sensitive system. The client then sends these requests to the load balancer. The load balancer distributes incoming autocomplete requests across multiple suggestion service instances. So then we have the suggestion service instances. Now in our architecture, as we can see, there are two suggestion service instances. The purpose of having multiple instances is horizontal scalability as well as availability. If the number of autocomplete requests increase, we can add more suggestion service instances behind the load balancer. But for now, we are keeping it to 2 because we also have to keep in mind our budget constraint. The load balancer also prevents one server from becoming a bottleneck. Now, once the request is distributed, it reaches one of the suggestion service instances that we have right here. Now, this suggestion service instance handles the actual autocomplete request. Its job is to receive the user's prefix and return the top 5 suggestions. For example, if the user enters app, the service needs to return something like Apple, Apple Music, Apple Store, Apple Watch, and application, let's say. However, the important design decision is that suggestion service does not calculate these rankings at the request time. Instead, it queries the Trie Cache where these results have already been pre-computed. This keeps online request path extremely lightweight. So the next component that we have is the Trie Cache. Now, the Trie Cache is the most important component for achieving our latency requirement. It stores an in-memory tree containing the pre-computed top K suggestions for different prefixes. A tree is particularly suitable for autocomplete because it represents strings character by character. For example, if the prefix that we received is app, the tree allows us to follow the path from A to first P and then from first P to the second P, like from A to P and then to the next P, and reach the suggestions associated with that prefix. The key point is that we don't need to search through all the stored queries. The tree already has been constructed and the top 5 suggestions have already been calculated. So the suggestion service simply performs the prefix lookup and returns those results. Because the tree is kept in memory, this lookup is extremely fast and helps us to achieve the less than 100 millisecond P99 latency requirement. The design expects roughly around 50,000 unique prefixes and approximately 200 MB of tree data in memory, which is a manageable amount for an in-memory cache. Now let's look at where the tree data comes from. So the system has a query log that stores historical search queries. Like whenever user performs searches, those queries are recorded. For example, the log could contain YouTube with very high frequency, YouTube Music with high frequency, and YouTube TV with low frequency. The frequency of these queries is important here because one of our functional requirements is to rank suggestions by query frequency. However, we don't want to calculate these frequencies every time a user types. That would introduce database queries and ranking operations directly into the latency sensitive request path. So instead, we process this information offline. Then in our architecture, we have something known as a rebuild scheduler. So a rebuild scheduler is responsible for triggering periodic tree rebuild jobs. It can run at predefined intervals depending on how fresh we want the autocomplete suggestions to be. And when the scheduler triggers a rebuild, it sends the rebuild jobs to the tree build workers or the tree builder workers. So next we have the tree builder workers. Now in our architecture, there are 2 tree builder instances that we have taken, and this allows rebuilding process to be distributed and processed in parallel. Now the important point is that it is an offline process. The user does not have to wait for the tree to be rebuilt before receiving autocomplete suggestions. Now these tree builder workers perform the actual aggregation and tree reconstruction. So these must be connected to our cache as well as the database. Now, when a rebuild job is triggered, the workers read the historical query data from the query log. They aggregate the frequency of different search queries. For example, suppose the query contains Amazon with 10 million searches, Amazon Prime with 5 million searches, and Amazon Login with 3 million searches. So the tree builder uses these frequencies to determine the ranking of suggestions. It then reconstructs the tree and associates the top 5 queries with each relevant prefix. So for the prefix AMA, we store the 5 most frequently searched queries beginning with the letters A, M, and A. The same process is repeated across the entire set of prefixes. Once the tree has been rebuilt, it is made available through the tree cache that we have. This creates the connection between our offline processing system and the online serving system. The final component is the monitoring and alerting component. Monitoring provides observability into the system. For suggestion services, we can monitor request latency, P99 latency, request throughput, error rate, and many more factors. For the tree builders, we can monitor rebuild duration, worker failures, and more. We can also monitor the overall health of our tree cache. So the tree cache can be connected with the monitoring service as well. If autocomplete latency crosses our 100 millisecond target or a tree rebuild fails, the monitoring system can generate an alert for this. This is particularly important because the system has both a latency sensitive online path and a background offline processing path. So this is the entire overall architecture, and let us now see the complete flow and put it all together. So there are two main flows in this system. First, let us go through the request flow. So for the request flow, whenever a user types a prefix, the request goes from the client to the load balancer, and the load balancer distributes the incoming request into one of our suggestion services that we have. Now the suggestion service then looks it up or looks up the prefix in the tree cache where the top 5 suggestions have already been pre-computed and returns those suggestions back to the client. Because the lookup happens directly against an in-memory tree, we don't need to query the database or perform ranking during the request. This is what allows us to target the sub 100 millisecond P99 latency. The second flow is the offline rebuild process. The rebuild scheduler that we have here periodically triggers the tree rebuild workers or the tree builder workers. The workers then read the historical search data from the query log and aggregate the search data along with the query frequencies, build the tree with the top 5 suggestions for each prefix, and update the tree cache. So the expensive aggregation happens offline while the actual user request remains extremely lightweight. The main trade-off here is between pre-computed top K suggestions and real-time aggregation. We are choosing pre-computation because latency is more important for autocomplete, right? The suggestions can be slightly stale between rebuilds, but in return, we get very fast and predicted prefix lookups. Overall, the load balancer and suggestion services provide us horizontal scalability. The tree cache gives us low latency lookups. The query log and the tree builders provide frequency-based ranking, and the rebuild scheduler keeps the tree updated. Monitoring and alerting gives us observability across the system, and they are all working together. That completes the total high-level design of a search autocomplete system, and let us now run it and see the output. So we can see that we got a perfect grade since we met all the requirements that we had to meet. We can also open the Murphy's Lab and check its performance. And when we exit Murphy's Lab, we get a performance report of our architecture. Also, we need to keep in mind that we can add more server instances or more tree rebuild workers. But since we had a budget constraint here, to keep our budget within the limit, we had to come up with this architecture or with this design right here. It can be optimized even more, but this is the most optimal design that we derived for this particular budget constraint. So that is the basic HLD of a search autocomplete system.